Section 6.2 is about the binomial probability distribution. This is a special case of a discrete probability distribution. The objectives in this section are: 1. Determine whether a probability experiment is a binomial experiment. 2. Compute probabilities of binomial experiments. And 3. Compute the mean and standard deviation of a binomial random variable. Objective 1 is determine whether a probability experiment is a binomial experiment. So binomial probability experiments have to meet certain requirements. First, the experiment has a fixed number of trials. Second, the trials must be independent, which means the outcome of any individual trial doesn't affect the probabilities in the other trials. 3, each trial must have all outcomes classified into 2 categories. We commonly refer to these as success and failure. And 4, the probability of a success has to remain the same in all trials. Now, the notation for binomial experiments and probability distributions is this. N denotes the number of trials, which we said had to be fixed. X denotes a specific number of successes in N trials, which means that X can be any whole number between 0 and N inclusive. And X here is our discrete random variable. P, and this is a lowercase p, denotes the probability of success in one of the N trials. 1 minus p denotes the probability of failure in one of the N trials. And one thing to notice here, since we can only have 2 outcomes, either success or failure, those 2 outcomes are complementary events, and that means that their probabilities have to add up to 1. So that's why we have p for the probability of success and 1 minus p for the probability of failure, because those 2 are complements of each other. Finally, an uppercase P of X denotes the probability of getting exactly X successes among the N trials. Now here are some hints for binomial experiments and probability distributions. First, be sure that X and P both refer to the same category, being called a success. So when you're looking at a binomial experiment, decide which outcome is going to be a success. The number of successes will be your X, and the probability of that success will be P. So both the X and the P have to refer to that same outcome. Also, when we're sampling without replacement, we consider events to be independent if N is less than 0.05 times capital N, which is the population size. In other words, if the population is large enough, sampling with or without replacement doesn't make a significant difference in the probabilities, so we ignore this requirement. Here's some examples of identifying binomial experiments. So which of the following are binomial experiments? The first one is that a player rolls a fair die 10 times. The number X of 6s rolled is recorded. Now this one meets all the requirements. We have a fixed number of trials, which is 10. The trials are independent because we're just rolling a die each time. The outcome of one trial isn't going to affect the outcomes of the others. We only have 2 possible outcomes, since all we're recording is how many 6s got rolled. So the only thing that we care about in each one of these trials is whether a 6 came up or not. That gives us 2 outcomes. And finally, the probability of success is going to be the same for each trial. Okay, part B, it says in a class of 30 students, 55% are female. The instructor randomly selects 4 students without replacement, and the number X of females selected is recorded. So here where we're selecting without replacement, we have to think about whether we can ignore the requirement or not. So here we're looking at the population size being 30 and the number of trials is 4. Our requirement says that if the number of trials is less than 0.05 times the population size, we can ignore the requirement. But in this case, if we take 0.05 times 30, we get 1.5. Our number of trials is greater than that, so we cannot ignore that requirement. The students would have to be selected with replacement for this to be a binomial experiment. So it's not a binomial experiment. Okay, and last of all, 10 M&Ms are selected from a bag with replacement, and the color is recorded each time. And this one, because we're recording the colors, that means that we have more than 2 outcomes for each trial. Most varieties of M&Ms have 5 or 6 colors, so we would actually have 5 or 6 possible outcomes for each trial. That means it's not a binomial experiment. Objective 2 is to compute probabilities of binomial experiments. And let's look at some methods for finding binomial probabilities. We will use technology for this, either your TI-83 or 84 or StatCrunch. There is a formula for binomial probabilities. You might see this in some of the MyMathLab homework examples, but I will not require you to use this formula. You can use your TI-83 or 84 to get these probabilities, and it's much easier. Now, the other thing we have to talk about with binomial probabilities is how to translate the wording to math symbols. So let's look at some different phrases and the math symbols that they translate to. So the phrases at least, no less than, or greater than or equal to all translate to the greater than or equal to symbol. The important thing to notice here is that there's an equals with this. So whatever the number is here, it would be included in the possible outcomes. The phrases more than or greater than both translate to a strictly greater than, which means that the actual number is not included. Fewer than or less than translate to this. And again, there's no equals symbol. There's no equals sign here, so the number is not included. No more than, at most, and less than or equal to all translate to this less than or equal to symbol, which does have an equal, so it does include the value. And finally, exactly, equals, and is all translate to an equal sign. Now let's look at how to use your TI-83 or 84 calculator to find binomial probabilities. What we're going to use to start with is this function in your calculator. It's binom PDF. And to get to it, you press the second vars key to get to the distribution menu. The binomial PDF function is the 11th one down on the list, so you have to scroll down to see the second screen in order to find it. So if you want to use it, you just highlight it and press enter. You will either see binomial PDF parentheses come up on your screen, or you will get this screen, depending on what kind of calculator you have. In either case, you need to fill in n, p, and x. If you got the binomial PDF with parentheses on your screen, put in the value of n, a comma, the value of p, a comma, and the x, and then add a closing parentheses. If you got this screen, just put in the different values and enter until you get to paste, and then enter again. If you put in these values, you should get this answer, 6.561 times 10 to the negative fifth. Now, once you've gone through this process once, you can get the function on your screen again by pressing second and enter. Then you can just backspace and change the values in the parentheses to get a different binomial probability. So that's kind of a shortcut that you can use. Let's do an example. According to the Experian Automotive, 35% of all car-owning households have 3 or more cars. In a random sample of 20 car-owning households, what is the probability that exactly 5 have 3 or more cars? So first we need to identify this as a binomial experiment, or not. Let's look at those requirements. First of all, there are a fixed number of trials because our sample size was 20, so n is equal to 20. Second, since the population of car-owning households would be extremely large, we can ignore the requirement of selecting with replacement. Now the 2 outcomes for each trial are success, that there are 3 or more cars in the household. Failure would be that there are not 3 or more cars in the household. And those are the only 2 possibilities, so we do have our 2 outcomes. The probability of success for each trial would be 35% because, according to Experian Automotive, 35% of households do have 3 or more cars. So our P would be 0.35, and we're looking for the probability that exactly 5 have 3 or more cars, which means we're looking for exactly 5 successes. This translates to x equals 5. So what we want to find is the probability of x equals 5. On your calculator, you'd use this function, binomial PDF, and put in the n, the p, and the x, and you should get 0.1272, and I rounded this to 4 decimal places. Second question. In a random sample of 20 car-owning households, what is the probability that at most 5 have 3 or more cars? So this is the same problem. We've already figured out that this qualifies as a binomial experiment. Now we just have to translate the at most 5. This would translate to x is less than or equal to 5. So that's what we want to find, is the probability that x is less than or equal to 5. So the outcomes that would be included here would be anything from 0 up to 5. So one thing to remember with binomial probabilities is that the outcomes possible for the experiment always start with 0 and they go all the way up to however many trials there are. So the outcomes in this particular event that we're interested in would start with 0 and go up to 5. Now all these different outcomes are mutually exclusive because we can't have both happening we cannot have 2 of them happening at the same time. So we can use the addition rule that we learned in Chapter 5. That means that the probability that x is less than or equal to 5 is the same as the probabilities of each individual value all added together. Now that looks like a lot of work to do on your calculator. If you use the binomial PDF function, you'd have to use it 6 times and add all the values together. So we're going to look at a shortcut. There's another function that deals with binomial probabilities that's binom CDF. This finds the probability that x is less than or equal to c for whatever value of c you enter. So to use it here, we would want to enter binom CDF of 20, 0.35, and 5 because we want the value for x less than or equal to 5. And the value, if you do this on your calculator, you should get 0.2454. Third problem. In a random sample of 20 car-owning households, what is the probability that at least one has 3 or more cars? Here, at least one translates to x is greater than or equal to 1. So we're trying to find the probability that x is greater than or equal to 1. Now if we think about what outcomes this would include, that would include all of the possible outcomes from 1 all the way up to 20, which was our number of trials. And the binom CDF function calculates less than or equal to instead of greater than or equal to. So this doesn't really fit with that binom CDF function. The only other way we could do this would be to use the binomial PDF function for each one of these 20 values, which again would be a lot of work. Here it would be much easier to calculate this answer using the complement rule. The complement of the event at least one success is no successes. That would be x is equal to 0. And we can very easily find p of x equal to 0, and then we would subtract it from 1 to find the value of its complement. So if we find the probability that x is equal to 0 using our calculator, we'd put in 20.35 and 0, and we get 0.00018. If we round this to 4 decimal places, we get 0.0002. Now, to find the value for p of x greater than or equal to 1, we take this value and subtract it from 1. So we would take 1 minus 0.0002, which would give us 0.9998. That would be the probability that at least one of the 20 households in the sample has 3 or more cars. Objective 3 is to compute the mean and standard deviation of a binomial random variable. Now these formulas are some of the nicest ones in this whole course because they're really easy. For a binomial distribution, the mean of the distribution, or the expected value, is just n times p. The standard deviation is the square root of n times p times 1 minus p. And remember, we're talking about a binomial distribution, so n is the number of trials, and p is the probability of success in any one of the n trials. Here's an example. According to the Experian Automotive, 35% of all car-owning households have 3 or more cars. In a simple random sample of 400 car-owning households, determine the mean and standard deviation number of car-owning households that will have 3 or more cars. In this one, our sample size was 400. That's the same as the number of trials. So n is equal to 400. We're going to define success as the household having 3 or more cars. So p, our probability of success, would be 0.35. So the mean of this distribution is n times p, which is 400 times 0.35, and that is equal to 140. To interpret this, remember that this is the same as the expected value. So in any group of 400 households, we would expect that about 140 of them would own 3 or more cars. The standard deviation is the square root of n times p times 1 minus p. So if we calculate this, we would get 9.5 for our standard deviation.